Alright, now that we have some understanding behind fundamental frequencies and overtones, let's go back to our sonometer question. In our question, we have a sonometer wire, okay, that's being hung by a weight of 5 kilograms. And it said it causes the string to vibrate with a fundamental frequency of 50 Hz. So it's given that the fundamental frequency of this sonometer is 50 Hz. That's the smallest frequency available, and all the other frequencies will be harmonics of this. So all the harmonics are available, but the smallest one will be 50 Hz. Okay. Now it's given if the length of the wire is halved, so you decrease the length of the wire, and another 5 kilogram mass is hung, find the frequency of the third harmonic. That is what is asked to us. Okay, now let's think about this. What happens when you decrease the length of it? Well, when you decrease the length, our fundamental frequency is going to change, because we saw that we saw the formula, right? The formula was F equals NV by 2L. So notice that the fundamental frequency purely depends upon the length. So the length changes. But what is also important is they have changed the mass. How does that affect? Well, that affects the velocity of the wave, right? That affects the velocity of the wave. So let's write the formula in terms of, we know what the velocity for the wave is, right? The velocity of the wave is given as, so we're going to write this as n by 2L. And we're going to write this as V is square root of t divided by mu. Okay. Now, what are the things that are going to change in our equation? L is going to change because the length changes. Tension is also going to change because the mass is increased. But mu is a property of a string. It doesn't depend on the mass or the length. It's mass per unit length, right? So mu is a constant. So I might as well say that our frequency is proportional, at least the fundamental frequency, I'm going to call it F1, the fundamental frequency is proportional, I'm going to put n equals 1, is proportional to root t divided by L. And we're going to use this equation to solve our problem. Okay? So, let's say the tension over here is T and the length is L. Then, the length is shortened and the tension becomes double because you put twice as much as mass. So, what's the new frequency? Well, F2, that's the new, I'm going to call this F1 dash or F1 prime. That's the new fundamental frequency. Divided by F1. This is the old fundamental frequency. The fundamental frequency of this guy. I'm sorry for the color mismatch. Yeah, I'm sorry about that. Anyways, that has to be equal to proportionality. So you'll have root T dash, that's a new tension, divided by L dash, that's the new length, multiplied by root T L. I hope you were able to get this. Frequency is proportional to root of tension and it's inversely proportional to the length. Okay, with this, we can get it. We can get the fundamental frequency. The fundamental frequency, new fundamental frequency is going to be the old fundamental frequency, that's 50, into root T, that's double, right? So that is 2T. And the new length is half. So that's L divided by 2 times L by root T. I'll get a root 2 divided by 2. And therefore, that is 1 divided by root 2. Sorry. 2 goes on top. Okay. So you get 2 root 2. So the new fundamental frequency, F1 dash, is going to be 100 root 2 Hertz. But the question is not the new fundamental frequency. The question is the third harmonic. Well, that's easy. That's 3 times this value. That's going to be 300 root 2 Hertz. Ta-da! There's our answer. Let me put a red box to it. So I hope you're able to follow. So if there's any confusion, this is the old fundamental frequency for this system. And this is the new fundamental frequency. I first calculate the fundamental frequency by putting n equals 1. And once I have the new fundamental frequency, The third harmonic is just 3 times that. Okay, that solves the problem.